Hi and welcome to this video. Now we want to talk about training of hybrid models and how it is done. And basically, again, we have different structures which we need to train, and they come with different challenges. So if we think about the parallel structure, usually the issue is, okay, you already have an idea about these theta2 values. So therefore you say, okay, this is sure. And now your issue is, okay, you want to train this theta1. And there are some specialized algorithms to train data-driven models. But usually what you need is the input and the output of the data-driven model. Now, what you have when you train such a model is you have some inputs you used to measure data, and you have some measured data, which I call theta with that head. So this is why this is my dependent output measured. And now my challenge is I want to calculate back from that output. So what I could do is say I change the calculation direction and say, okay, I have this output. It's my output of the white box model. It's my G from U2 and theta2. And this is subtracted from my measured inputs. So different direction. And these values I feed back to the output of the data-driven model. And I call this Z. With this configuration then, it should be possible to train my model, and the basic training objective could look like the following. You have your theta1, and this equals the argument from your optimization problem, where you minimize with help of these parameter values theta. The norm could be a kind of distance, could be like square difference, but also you could use a more specialized algorithm which basically still needs or tries to minimize this offset between this output and this input. And yeah, the norm of this output minus what is coming out here, and this is basically f from u1 and theta1. This is some kind of norm with, and here I write down Z. I already explained it. This is the difference between the measured values minus what you get from your white box model. Now we have a look at the serial one. Here again, we have the challenge, okay, we might in one case want to fit only the parameters of the black box model, so question mark, and the white box model might be known, and I have my measured values with the head. And now if I want to train the black box model, I have to invert this and say, okay, my measured values feed back, and then I aim to also provide the values at the output of the black box model, which I call then Z. And I have my output function, which depends on u1 and theta 1. So what you can clearly see, z is not like a difference anymore, so it's a little bit more complicated. If you would write down the training objective, this would be, or could be, in general, something like your theta 1 again is the arc minimum minimized with theta 1 with the norm of z minus what comes out here, so u1 theta 1. But now with z equals the inverted function u from u2 and theta 2 times my measurements y hat. And what you clearly see is that the condition is that this function g from u2 and theta 2 must be invertible. And this approach is called actually the direct approach if you are talking about the training of the data-driven model. So it's direct approach for training you have to be a little bit sensible here, because if you talk to people from process systems engineering who are using hybrid models, they might also talk about indirect identification related to this kind of model architecture, because what they mean is that they firstly estimate the derivatives of the or within the balance equations they use to then have the feed for the black box model, and this is actually then called an indirect identification. But if you are talking in terms of the data-driven model, you want to, or you have a direct training of the data-driven model, so don't get confused. Now, another case might be if you want to fit both parameter sets, so theta 1 and theta 2, or if you have not the opportunity to invert G, then you might need another approach, and this could be work as follows. You have again your measurement values. These are fed back to the output of the white box model, but then you don't go further back. You just say you have your output G from F from U1 and theta 1 and U2 and theta 2, and then say for the training objectives, that in the case you are just training theta 1, you would say theta 1 is equal to argument of the minimization with theta 1 from the norm of my measured values minus G from F from U1 and theta 1, U2 and theta 2. Or if you say you want to fit both, you might have this set of both parameter vectors, which you can then like estimate with the argument minimization dependent on θ1 and θ2, and then you have again the same term, so it's again y hat minus g from f u1 θ1 u2 θ2 and this null. So, and as I said above, so you use this when g from dot is not invertible, and this is called then the indirect approach. For the data-driven model. And here you clearly have to say, if you would talk to a process engineer who is using hybrid modeling, he might talk about direct identification for the overall model. If it, is a model of, maybe here you have a data-driven model for kinetic and here a mass balance or something, so a balance equation, then this would be called a direct identification, but it's the indirect approach for the data-driven model training. Sometimes people also call this the sensitivities approach, so also called sensitivities approach. That's it for this video. Thanks for watching, and I see you in the next one.